Ngalakin Khadijan Nyunga Boja.
Okay, it's time to look at financial side of things. Everything we do in mining engineering has to work safely, environmentally responsibly, but also we're there to make a profit. So we need to think about the financial side of things and compare different projects, different options. Obviously, this is a whole field of economics, but it is something as a mining engineer you do need to know and maybe understand to a greater degree than most other engineers. The costs of things are really important. So some of the things I'll talk about, cash flow modelling, revenues, operating costs, net cash flow, discounted cash flow, which leads into NPV, internal rate of return, payback period, and some comparative measures. So cash flow modelling is where we try and model the amount of cash that's expected to flow in and out of a project. Obviously the cash coming in is good stuff, going out, cost is the bad stuff. Cash is a nice consistent way to compare different project types, so we can compare different metals rather than talking about, oh, this mine produces so many pounds of copper, this mine produces ounces of gold, and this mine produces 1 million tonnes of iron ore. Very hard to compare, so money is the common denominator. Same with different countries, allowing for exchange rates and different mining methods. We tend to focus on cash coming in and out rather than profit. Profit is an accounting term, and although purely, and I've been using in this unit as a difference between revenue and costs, it is an accounting term and as such can be manipulated legally and is not quite such an independent tool. Cash is something we can sort of see and feel in the accounts. So all this work helps us predict the money we will spend, the money we need to have to get the project going, and hopefully the money revenue we will receive in the long term. It helps us choose between different projects. If we've got 2 different projects, which of these 2 would you invest in? We've got Project A, which lasts 6 years, cost $80 million to start, and then has cost every year $20 million and revenue $50 million. So that sounds good, but this is better than Project B, which only lasts 3 years, costs $50 million to start with, and then has costs and revenue of $10 million and $50 million respectively. Which one is better? And you can look at those numbers and make a bit of a guess, but let's try and do this a bit more scientifically and quantitatively. Just on revenue, it's important to note what you're selling. And that might sound a bit strange, but as a mine, you produce ore, and you can sell the ore literally at the mine gate, and then it goes to another operation which concentrates, which then sells onto another operation which produces pure metal. Now you might go all the way through that supply chain and sell the pure metal, or you might stop here and sell the ore at the mine gate, or you might concentrate it and sell the concentrate. And it's important to recognise where you are in that supply chain. That's obviously what you sell and is the revenue you get. And you might decide where you want to be on that supply chain. So you might just mine it as ore, so the mines near Kalgoorlie, Kambalda, nickel mines, which produce ore and sell it to the concentrate, which is nearby, and that's shared between several small mines, but the owner of the concentrate is a separate company. And they produce concentrate, which in the Kambalda example then gets sent down to the concentrate, then goes to a refinery, nickel refinery at Kalgoorlie, and then goes to the smelter at the Kwinana. And anywhere along that, you can sell your product onto a different company. And if vertical versus horizontal integration, although it's displayed horizontally in this diagram, if you own the mine, own the concentrator, own the smelter, own the refining, and sell the metal bars, that's called vertical integration through the whole operation. Even more so if you then produce the jewellery or the batteries or whatever, so it's sold to the customer, end customer, arguably. Of course, that battery might then go into a Tesla car, so the end product is actually a Tesla car. So it gets sometimes a very long supply chain. But if you try and own all of that, so if Tesla tried to buy lithium mines so they could secure their supply of lithium, they would be vertically integrated all the way to the final car. Horizontal integration is where you don't try and do that, but you try and maybe produce the best lithium batteries in the world. So you buy lithium ore from mines, you don't own those mines, but you try and buy the product from a lot of mines and you produce a lot of lithium batteries. You try and dominate the lithium battery market. So that's horizontal integration. And these are strategic things companies think about, whether they want to be vertically integrated to try and, in particular, secure their supply, or horizontally integrated and dominate one market. Revenue equation can be quite simple. That's the price you get per unit metal, less any selling costs. So that might be costs like transportation. So if you're selling iron ore, generally it's sold not at the mine gate, but at the port. So you've got the cost of the train to take it to the port. You might have some marketing costs, things like gold. There's a ready market for gold. But if you're producing 5,000 tonnes of copper, you can't just waltz up to somewhere online and sell that. Generally, you need to find markets for it. People are going to buy it, same with lithium and so on. And often you do this as part of the setting up the mine, so you know you've got a customer. You might even lock in the cost, the price, so you know how much you're going to get. The average grade of the ore, and the fraction, the metallurgical recovery, and the tonnes of. It's a trivial example here. And it's important to note, of course, it's fairly sensitive to the average grade. So the average grade goes from 3.5 up 10%. The revenue will go up 10%. Similarly, the processing recovery, if you can get the processing recovery from 85 to 86%, you actually get an extra $12 million per year. So that's pretty large numbers. So if you can buy a machine, which might cost you $50 million, but it increases recovery from 85 to 86, $50 million, you'll pay for that in about 5 years. Capital costs, you've probably heard this term, buying equipment, plant or land that's used over many years, but you pay for it once at the start, generally. Capital costs are depreciated for tax and profit accounting purposes. We spread it over the life of the equipment, and generally we just use a simplistic straight line, which is what you should have done, but lots of you didn't in the assignment. Take the cost and spread it out the expected 10-year life or 6-year life of the mine. And we tend to keep it simple. Cash is more important than profit, so we generally don't get involved with any fancy depreciation. This depends where you are in the world, and different depreciation laws a tax office lets you do. Capital costs incur before we get any revenue, so before the first train of ore, gold bar is sold. They're called pre-production capital costs. And these are really important because these are things you've got to pay for before you've got any revenue. So you've got to borrow the money or have the money already to pay for these, or you can't start a mine. So if you can't get this money, you can't proceed. Doesn't matter how good it is, unless you can borrow it from the bank. Pre-stripping of waste. So usually the ore will not be on the surface. You'll need to remove some waste. There might be 10 metres, might be 100 metres. And sometimes that's called a pre-production capital cost. And we usually flag these sorts of costs as occurring in year 0 of a project. Capital costs incurred once we're up and running, say typically replacing equipment after 6, 7, 8 years, whatever it is, can be called production capital costs. These are less important, that's probably the wrong term, less of an issue as we've got revenue coming in, so we're generally getting some lots of cash coming in, so we've got the money to pay for it. We don't have to dip into our pocket or borrow from a bank. Operating costs are costs which happen and are used in the period. Generally, period in this case is a year. So typically things like labour, fuel, parts, electricity, often expressed as cost per tonne mined, sometimes cost per tonne of ore, or sometimes purely cost per year. Things like salaries would be a cost per year. They are the same irrespective of how many tonnes you mine. Fairly obviously, if the revenue we're getting is less than the operating costs, then we're in trouble and we're losing cash and you can't continue. That might be acceptable for a short term if you are confident that the revenues are going to increase, that the price is going to increase or the costs are going to reduce for some reason, then you sometimes are prepared to accept a loss over short periods. So let's say we mine 10 million tonnes a year at $2 a tonne. We process 5 million tonnes a year at $10, $12 per tonne. And we have $2 million of what's called fixed costs, time costs, independent of how many tonnes we have, which might be our salaries. So the total cost is 10 times 2 plus 5 times 12 plus straight 2, 82 million a year. So that would be our operating costs, which we might then term as $8.20 a tonne or $16 per tonne of ore. You can phrase it in different ways. All right, now let's look at these sorts of things, the cash flow, and look at it over several years. The net cash flow is quite simply the cash coming in, revenue less the cash going out, costs. So that's quite simple. It's useful for just determining if the operation is viable, whether we have any periods when we're going to need to borrow money, etc. And we would do this for each period, normally a year, over the life of the mine. Remembering the parameter can vary from year to year. Typically the grade, which directly impacts our revenue, will vary, which is why we want out of the mining plan, the mine design, an idea of what grade we'll get every year. Mining costs may increase with depth, as you've seen in the assignment. Processing costs may increase as rock gets deeper, which tends to get harder, so need more energy to fragment it. But costs may decrease as the operation becomes more efficient, and they should. So as you get more experience with the mining equipment, your processing, you should, and you pay engineers to do this, become more and more efficient. So let's do an example. I've described this one before. Project A, 6 years. Project B, 3 years. If we display it in a simple tabular form, so the years, year 0, so this is the pre-production capital costs. So we got Project A, we got 80 million. We got no operating costs, we haven't started operating yet, and we got no revenue, we haven't started producing. And then for each of the 6 years, operating costs are 20, revenue is 50. And Project B is similar, but only 3 years long. Which one of those would you choose? Let's look at the cash flow for each year. Quite simply, we just add up numbers in a year. So we got minus 80. Year 0, year 1, we get plus 30, and so on. So pretty simple. And then if we add all those together, we get 100. If you add minus 80 plus 30, 30, 30, 30, 30, we get 100. I've actually, as a check, added horizontally across there for each of these, then added vertically. So I can make sure I haven't missed anything. So we go net cash flow, this one 100 and this one of 70. So project A looks better. What about if we only had $60 million available to us? You'll notice in project A, we need to spend $80 million before we start to get any money. So we've got to have $80 million, either in our back pocket or borrow it from the bank. So if we can't, then option project A is just not viable. We'd have to sell the project or go to project B. The problem with using net cash flow is it doesn't account for the timing of when money comes in and out. So we've looked at our cash flows here, and we've given the same significance to money coming in and out in year 1 as in year 6. So that's the problem. Does it matter when cash flows are received? Fairly obviously, yes. I wouldn't be saying this. So how do we cope with that? Let's look at discounted cash flows. This all works on the basis that $100 received today is worth more than the $100 received in 1 year's time. If I said to you, I will give you $100 now or $100 in a year's time, that's assuming you trusted me to give it to you in a year's time, you would take $100 now. Because in theory, you could do something with $100. You could put it in the bank and come out with $100.01. You could use it for enjoyment. You could use it to generate more wealth. So money today is worth more than in a year's time. So that means $100 in 5 years' time. How do we equate that to $100 in today's money? We do that by converting everything into the present value, or PV as it's sometimes called. We convert into equivalent today's money, and this is called discounting. And very simplistically, the present value of something is the future value times the discount factor. Wow. And the discount factor is this equation here, which has in it just the discount rate, which we'll come back to, and the number of periods, so the number of years. Now, the discount rate is a hugely important number in all projects, and something which accountants and economists will spend years arguing over, or constantly will argue over. It's expressed as a fraction, but described as a percentage. And it involves the interest rate you get from a bank. So that, as an absolute minimum, you could just put the money in the bank and you'll get whatever the interest rate is at the moment. Less than 1%, it's tiny. And if your project gets less than 1%, you think, why bother? We'll put the money in the bank. You also have things like the risk. So you're trying to, if you're in a high risk country, you want to have more return than if you're low risk. It's hard to turn that into dollars and cents, but it's just included in discount. Discount factors in mining commonly 5 to 15%. As I said, you'll see lots of academic papers and lots of views about what you should be using as your discount factor. So if we look at a discount factor, say with discount rate of 10%, for the obvious reason it's nice and simple. Discount factor for year 0 is 1, and then after 1 year, it's 1 over 1 plus 10%, or 1.1. So that's 0.91. And then it's 1 over 1.21 and 1 over 1.331, etc. And convert those into $1. So $1 now is worth $1. $1 in a year's time is worth 91 cents in today's money, and so on. And you'll see how it goes down fairly quickly. 10% is probably quite high in today's environment with interest rates at all-time lows. If we go to discount rate 15%, you'll notice it drops much more significantly. We show this graphically. That's 10% discount, so $1 today is worth $1 in 0 years, 91 cents in 1 year, and so on. So you see, it's not a straight line, but in 10 years' time, it's worth less than half it is today, and so on. The discount rate of 5%, it holds its value longer. Discount rate of 15%, it drops more. So it has a big impact. The interesting thing here is all of these, after about 20 years, got pretty small significance in today's money. So when you're designing things, don't worry too much about what's happening in 20, 30, 40, 50 years' time. It's not going to have a big impact on today's economic value. So worry more about what you're doing in the first few years. So we apply this discount to our cash flows for each year, acknowledging each year has a different discounted factor, and then we add up the numbers. And that gives us what's called net present value, which can be used to compare projects. So we do that for our typical example here. We look at the discount factor for years 1 to 6, at a discount rate of 10%. There's our discount factors. And then we simply apply that to our net cash flow. So we take the 30 and multiply it by our discount 0.91, 30 by 0.83, and so on. And we also include the 80 at 1. Easy to forget that. So this is our present value for each year. And then we simply add those up over the project life. So if you add those, minus 80 plus 27 plus 24, blah, 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 net present value of, what's that, 50? And net present value of 49. So you might have thought initially, project B is much better because we have to spend less. But in actual fact, net present value is slightly higher for project A. Got a couple of examples which will be on LMS. So very imaginatively called Project P and Project Q. See if you can tell me the net present value for each one of those using a discount rate of 10%. Of course, you're not going to hard code that discount rate in your Excel, are you? You're going to make that as a variable. Or you could have something a little bit more complex, Project X and Y. See if you can do that. And I'll put up solutions for these later. Internal rate of return. This is a really important number. To generate it's defined as the discount rate. So remember those equations you had in your Excel spreadsheet, you set the discount rate. If you could vary that, it's discount rate that produces a net present value of 0. And that shows you the amount of money you're getting back per amount of money you're putting in. So it lets you compare projects with vastly different initial investments. So it's very hard to tell, is a small profit from a small investment better than a large profit from a large investment? It's hard to make that decision. And NPV doesn't tell you. So the NPV might be $5 versus $10, yeah, which one's better? Because I might be able to have 2 of the smaller ones. So if we go back to our project A and B, if I said it's a discount rate such that net present value equals 0, so the easiest way, so the engineer's approach is to take your Excel spreadsheet and just vary the discount rate until you get a net present value of 0. So here's my spreadsheet, and I've calculated NPV as just the sum of the present values. There's an extra row here for cumulative NPV, so it changes each year, which we'll use later. And to calculate IRR,
we change the discount rate here and just keep an eye on NPV and change it till NPV becomes 0 for this project. So let's change it to 20%. Okay, 25%. Still more, 30%. Okay, so it's gone negative, so a bit less than 30%, 29. So somewhere between 29 and 30. And obviously I could play around for the rest of my life until I got exactly 0, but remember, better to be roughly right than precisely wrong. So that's probably close enough to 3 significant figures. But obviously there is actually a better way of doing it. There's a command in Excel called IIR, equals IIR. And then it asks for the values per period, non-discounted. So be these. Close bracket, 29.6, there you go. And if I copy that down for this one, 60.7. And just to check that's correct, I put up here 60.7. Yep, sure enough, NPV is almost 0. So that's it.
So the 2 ways of doing this, trial and error, or you can use the function in Excel, which is obviously easier, but I would suggest you never ever use that without checking it yourself. So now we've got another parameter, IRR, which is much healthier for project B. So project B, although it has less net present value, we're achieving that in a short time frame, so that's maybe a better use of our money. And maybe go back to project P and Q and determine the IRR for those and for Y and X. One other useful parameter is something called payback period. This is pretty simple, and it's to do with you borrowing money from the bank or anybody. They'll generally want it back as soon as they can. Payback period is basically when the cumulative net present value becomes positive. So you've actually got cash, you've got a positive cash flow, and you've got cash in the bank. So the shorter the payback period, the better, but it's not a fixed thing, and banks will be prepared to lend you a payback period 10, 20 years if they've got confidence in you. And as I mentioned, it's easy to determine. You do a cumulative net cash flow, and when that becomes positive, that's when you're able, in theory, to pay back your loan from the bank. So if we look at our A and B, and I've added an extra line here, the cumulative present value. So we start off with minus 80, then we add 27, add the 24, and so on. And eventually it should end up with the net present value we calculated before. And where it goes from negative to positive sometime in year 4, that means we don't have to borrow any more money. We can pay back the bank, so the payback's year 4. And similarly, this one is year 2. So it's not a big thing, payback, but if you will find it easier to borrow money if you can say, we're going to pay you back in 2 years' time. So we use all of these tools. The most common ones, we look at net cash flow, net present value, IIR, and payback. Those are the things we generally look at for most projects. Big projects, obviously, you can go into a lot more detail, but even small projects, not a whole mine, but just we want to expand the mine in this direction, we want to open a new stope, we'd look at these. So if we go, remember our projects A and B, we just looked at the cash flow. Project A was better. We looked at NPV, project A was slightly better, but IRR turned it around, and project B became much more attractive. Which is the most important of those measures? It's NPV is the most commonly used. It has its failings, but it's the most commonly used, everybody understands it's easy to calculate, etc. But generally you'd use others as well. IRR would be a very close second. But of course, it's not as simple as that. It's not just simple as pure numbers. It depends on the nature of the decision maker, the company you are, the attitude to risk, what your objectives are. So we had this, is our objective just to make as much money as we can very quickly and get out of there? Or do we see a long-term relationship with the local peoples, in which case we want to have a longer-term viewpoint and we're not quite so hungry for just profit? And how much risk are we prepared to take? How much money do we have? How much can we borrow? What experience do we have in this project? So we've got a fantastic underground mine, but we are surface mining iron ore people. We haven't got a lot of expertise. It might be better to either employ people with expertise or to sell it. And what were the alternatives? What are the other projects we could do? What are the plans for our company? So it's never quite as simple as just NPV, that's it. The more vague things would need to be considered. All right, I'll put up solutions to those little tutorials later.